Okay, we are back, and this time we are going to talk about truth trees. Just before we started recording this, we were trying to do a proof using the natural deduction, but it got a bit like you need to pay a lot of attention when you're doing any kind of proof, whether you're doing natural deduction or whether you're doing truth trees. Um, and once you pay attention, the problem is kind of easy. It becomes pretty easy, straightforward, right? So one of the proof strategies that we discussed earlier is so we have like a semantic entailment, and we have a syntactic entailment. Um, Semantic entailments are like truth tables. Truth You can prove semantic entailment using truth tables and truth trees. Syntactic entailment, you can prove it using the rules of inference, that we rules of inference or the rules of um, equivalence. Now the thing is, you can derive any rule of equivalence from the rule of inference, so that's another thing. um, Using all of these techniques, you can sort of get it done. So the thing is, with propositional logic, if you can prove something is semantically entailed, it just follows that it is also syntactically entailed, because propositional logic is both a complete and sound logical system, or like a formal language. And completeness and soundness just refer to this property. So if a language is complete and sound, it just means that if something is semantically entailed, then it is syntactically entailed, and if something is syntactically entailed, then it is semantically entailed. So the advantage with truth trees is, if you can prove that something is valid, or like an argument is valid or invalid using truth trees, you've automatically proved that it is going to be valid or invalid using the rules of inference or whatever, because one entails the other, right? So so truth trees is actually like a very very useful technique for as a proof strategy, because it's kind of simple to learn. It's it's a bit difficult to apply, but with practice you just get it very easily. um, and the basic idea behind truth trees is similar to that of the indirect proof, where you take the negation of the conclusion, and then you proceed from there. That's kind of the idea. Now, truth trees are also called by a second name called semantic tableau. Semantic tableau. Um,
Yeah,
that's
it's a French word.
Yeah, it's a French word, semantic tableau. I think it's a derivative from something to do with a table or something like that. I don't know.
Yeah.
Yeah. So before we do this, let's lay out certain important things. So one important thing is all the symbols we are going to be using. So just like in propositional logic, we have propositional variables. So we're gonna use p q r, p q r, etc. All the symbols that we would use in propositional logic as propositional variables, we are allowed to use it over here. The other set of symbols is obviously the operators, the and, or, um, the implication, the biconditional. Now notice that I'm not putting the exclusive disjunction here, because the exclusive disjunction is just going to be the negation of the biconditional. So if you have alpha exclusive or beta, this is the same as alpha. The negation of alpha implies beta. Sorry, the double implies beta. So these are equivalent. So wherever you see something like this, you can just convert it, and then you can proceed over here. Um, I'll also tell you how to do it without doing that. Um, but yeah, just remember that. So that's the second set of symbols. The other set of symbols, which are going to be new, is gonna be a bottom symbol. So this is a bottom, so you have like a standing line and like a horizontal line, which is like it's sort of like an inverted T. Okay, this is called bottom. And then you have a top. This you will hardly use this symbol, but I'm just giving it to you for like a reference. And then you'll be using cross. So this cross symbol and the bottom symbol are kind of interchangeable. But yeah, this is something we will be using as well, which is why I'm showing it here. Okay, so we are done with the symbols. Now we need to talk about certain rules. Now the rules are going to be very similar to the rules that we already have learned with slight variation. So in rules you have two categories. Horrible straight line. Yeah. Okay. So you have the alpha rules and you have the beta rules. Alpha rules and beta rules are the same thing, except beta rules are the negations of the alpha rules. That's all it is. So alpha rule number 1, not P entails not P. This is very straightforward. So wherever you see a not P, you can just replace it with a not P, obviously. If you see a P and Q in a truth tree, you need to write it like this. So, stack them one over the other. Ideally what you want to do is you want to draw a line and then you write P and Q. So that's the second rule. The third rule is where the tree portion in the semantic tree, the truth tree thing comes in. So wherever you see P or Q, wherever you see a disjunction, you just draw a split. And the split is gonna be a not P, it's gonna be like a P or Q. So this is just telling you that there are two cases. So there is P case and there's a Q case. So it's sort of like a branch, like a dichotomous branch. And then you have the P implies Q, where also you have a branch, but here you have P, not P or Q. You get this because, you can apply the material implication rule, and then you attain a disjunction, and the disjunction is of the form not P or Q, and so you can just take a shortcut and write it like this. That's fine?
Yeah.
Okay. And then the last alpha rule is this, which is to say P and not Q, or not P and Q. Is that fine?
So you've got P. Okay, so you split it and then you've got two sort of conjunctions.
That's right. Yeah. Oh, wait. One sec. Sorry. I messed up. That's the beta rule. I wrote the beta rule instead of the alpha rule. You get this. So you get a split. You get P and Q, and then not P and not Q, right? Because from this direction you get not P or Q. From this direction you get Q or not P, right? So not Q or P. Sorry. Yeah. So you get it like this. Basically, yeah, you get it. This direction is gonna give you one conjunction. So you get P or not Q. Sorry. Not P or Q in this direction, and then in this direction you get not Q or P, right, in this direction, and then you can just put them like this, right?
So why did you put the not P on the right hand side?
Yeah, so you can also write it like this, right? You can also write it as so what does a biconditional mean? A biconditional means that both of the um, both sides of the biconditional, both the atomic propositions are both simultaneously true or simultaneously false, which means both P and Q and this thing, right? As I told you before, the material equivalent, sorry, the making conditionals rule, but just backwards. So when we say P if and only if Q, we are saying that P and Q are both true or they are both false, right?
So if they're both false, it's a truth. It's true as well, right?
Yeah,
And
if they're both false, then the conditional is true, a biconditional is true. If they're both true, then the biconditional is true.
Yeah.
So that's why you have two possibilities. They can both be. So when you say a biconditional is true, you have two possibilities. Either they are both true or they are both false. So that's why you
Yeah.
have a branching there.
Yeah.
Okay. Yeah. Just to make sure that we are still rolling. Yes, we are. Okay. Cool. Yeah, and this beta rules are just going to be negations of the alpha rules. So you get not P.
So that's what just beta means, that it's a negation of the
Yes.
alpha rule?
Yeah.
Okay.
So yeah, so you get not P instead of not P because it's a negation, right? So you get P, right?
Yeah.
Then you have a negation of the conjunction, which means you can apply a De Morgan's law and then you get a disjunction, right? So you get not P or not Q, right?
Yeah.
Yeah. So I'm just applying a De Morgan's law here. So it's going to be not P or not Q, and because it's an or, there is a branch. Yeah.
Mm-hmm.
Yeah. And then you have P or Q, right? What's this going to be?
So then we get a conjunction from them, so it's going to be going down.
Yes. So that's what you're gonna get with a small, like a branch kind of thing. And then you have the conditional. What are you gonna get here?
Negated.
The negated conditional, right?
So can we first do a material implication, then negate it?
Yeah.
So we get so 1 minute negated, and then
So what's the false condition
not
for
P.
yeah, don't do the De Morgan's law in your head. Whenever you see a false so whenever you see a negated conditional, you just need to remember the false condition of a conditional. When is a conditional false? When the antecedent.
When the is true and
Mhm.
the condition the consequent is false.
Exactly. So what's it going to be over here?
Oh, do we need to do the opposite of it because it's a negated, or
No, it's so the negation. It's already negated, right? Which means the implication is false. So what does it mean for an implication to be false?
when it's false, it means that what I just said basically, that
Yeah.
when it's when the antecedent is true.
Yeah. So you don't need to do the negation again.
Okay, so it's just like the antecedent is true and the consequent is false.
So
So
yeah,
we do a conjunction.
yes. So you get P and not Q, right? And then you have the last one. What's this gonna be?
So we do De Morgan's law on it.
No?
So we just do what we did for the last one. So we
Yeah.
just so when is the biconditional is false when they, for example, when alpha is true and beta is false, or the other
Yeah,
way around.
sorry. I put alpha and beta here, which is what I should have done for the others, but it's okay.
E and Q, yeah.
Yeah. But for the sake of maintaining consistency, I'll just change this because I can't be. I don't want to go back and change everything. But yeah.
Yeah.
So you have a branch here, and then
Yeah, so
yeah.
it's like P is true and Q is false.
Okay.
And then on that one, Q is true and P is false.
Exactly. So yeah, so these are the alpha rules and the beta rules. Now notice that some of these have a branch and others don't have a branch, right? For example, I want to use golden. This, this are branching rules because there's a branch, right? But
Right.
this are non-branching rules, right?
So the line above the conjunction above the P and the Q, that doesn't count as a branch.
No, it doesn't.
Okay.
So whenever you see a split, it's called a branching rule.
Mm-hmm.
I suck at drawing the curly brackets. Okay, so these are the branching rules and these are the non-branching rules, right? Over here, this one and this one are the branching rules, and all of these and this are non-branching rules. So you can also see like an inversion. Over here you have 3 branching rules. Over here you have 2 branching rules. Over here you have 2 non-branching rules. Over here you have 3 non-branching rules. Because it's a negation,
Yeah.
Yeah. So we have covered the rules for drawing trees now. So we are sort of ready to proceed and draw certain trees. So let me just, before we go there, I'll just lay down the stuff you can do with a truth tree. So what you can do is you can prove validity. I've already told you this in the previous chat, but I'll just say this for the recording. So you can prove validity or invalidity. You can show like a formula, a WFF is a tautology, and then you can show equivalence. Okay, so these are the 3 things you can do. We will try to stick to this for today, and we'll come back to the rest later. Okay, so let's sort of lay down a procedure, right? procedure for building truth trees. Step 1 is to just write down all the premises and the conclusion. Just write down all the premises, okay? And then you write down the negation of the conclusion. Just give me a sec. Yeah, I'm back. Okay, so let's do these steps and then we'll talk about the other steps. Okay, so let's take an argument that we know to be valid. So why don't you tell me, like, give me an example of a valid argument?
So modus ponens.
Okay, modus ponens, simple enough. So that's the first premise, and that's the second premise, and then the third premise is gonna be the conclusion, but I have written here the negation of the conclusion. Okay, now what you need to do is apply each of the branching rules to each of the premises. Now here we don't have to apply a rule for number 2 because it's already sort of done. Like it's just P and you'll just put a P, right? So it doesn't really matter. But for the other one, you need to apply a branching rule. So what's the branching rule that we will apply here?
So we branch it off into not P or Q.
Exactly. So you can put a branch over here and you can say not P or Q, right? That's the branching rule. And here you can write whatever rule you're applying. Let's say you're applying material implication. And you can also specify the premise. So you have this.
So that one I didn't really apply material. I didn't really apply material implication. I just applied the fact that it's true when.
Right. So yes. So you don't actually need to mention this, but like under the covers, that's kind of what's happening, right? Like you can just mention this is from P1. So you just applied some branching rule to P1. You don't have to worry about what inference rule you're applying because we are doing a semantic proof. But I'm just telling you, like, this it's the sort of basis for this is the material implication.
And then when you're branching it off, like, what does it, like, in words mean that what we're doing there? We are just showing, like,
there are two. So when we are doing like a branching, it's a disjunction, right? So we have two possibilities. So you can either go this way or you can go this way.
And then what are the possibilities referring to? Possibilities for that, for the premise to be true, or what? Like, what does it mean by possibilities?
Yeah. So when you say like a conditional is true, you just mean that either the antecedent is true or the consequent is false, right?
Yeah.
Sorry, the antecedent is false or the consequent is true, right? So that's just how it is branching out. So you can consider that the antecedent, you can consider the antecedent is false, or you can consider that the consequent is true, and that's all this branching is really doing here. Okay.
Okay.
Yeah. So now we are done with this premise. So we'll put a check mark over here. And this premise is already atomic. So we'll put a check mark over here. We don't really need to do anything about the conclusion. So because the conclusion itself is atomic, so we'll put a check mark over here. So we are done exploring each of the premises, and now we have arrived at the atomic propositions, right? So now notice this. What's this? It's not P, right?
Yeah, it's not P.
Yeah. Now if you take this root, if you take this branch, so to speak, let me show it to you with some cool effects. Sorry, one sec. So if I take this path, right, what I'm gonna get is a P, a P and a not P. So we have a contradiction there,
Yeah.
right? So I'll say that this branch is closed, which means it's this branch has ended up in a contradiction. So when I want to say that this branch is closed, I can either put a an X mark, or I can put a bottom symbol. My stroke width is too much. Yeah, so I prefer putting the bottom sign because that's how I learned it. So I'll just put this symbol, which means this branch is closed. Now let's go to the other branch.
That one looks closed as well.
That one looks closed as well, right? So I'll put a bottom here, and the reason it's closed is because here you have Q and here you have not Q. So oh sorry, yeah, so this branch is also closed. Now when all the branches are closed, it means that regardless of how you proceed, you are arriving at a contradiction, which means you have shown that if you negate the conclusion and keep the premises true, you will arrive at a contradiction no matter what you do, which means that the conclusion is not like it's not false, the conclusion is true given that the premises are true. So whenever you have closed branches, you have a valid argument. So when all the branches are closed, the argument is valid. Okay. Now I can try to show that to you by attempting to do this with an invalid argument. Do you remember constructive dilemma?
Yes.
Can you tell me?
So it's alpha implies beta.
Okay, I'm writing P implies Q.
Now for the second premise, we have R implies
R
S.
implies S. Okay. And the conclusion is supposed to be P or R implies Q or S, right?
But we also have normally we have a third premise as well, right? For constructive dilemma.
Yeah, you have that. You have P or R.
Yeah.
Right? And then the conclusion is R or S, right?
Yeah.
So let me just change that. The conclusion is Q or S, But let me just change that to R or S because I know that it's an invalid argument. So constructive dilemma is valid, right? What I'm doing is I'm just changing the conclusion. So the conclusion for constructive dilemma is P or it's Q or S, right? What I'm doing is I'm just changing this to make it invalid. I'm purposely making it invalid just to show you how an invalid argument would look in a truth tree. Okay?
Yeah.
Yeah, so this is the conclusion. So what I'll do is, so I have listed down all the premises. I'll list down the negation of the conclusion. Okay? Yeah. So, now you can start applying the rules for, yeah, you can start applying the rules.
This is a beta rule, right?
Yes, this is a beta rule. So yeah, okay, by the way, another thing I should mention is, you should first apply all the non-bonding rules. So see, the order of the premises doesn't really matter, right? uh, it doesn't matter whether you put the premise 1 as premise 2 or put premise 3 as premise 2. The order doesn't really matter, but to make the tree as efficient as possible, it's best to apply all the non-bonding rules and non-branching rules and then apply all the branching rules. So here you will first apply the here you know that this is a beta rule, and I know that this is a non-branching rule because here you have a conjunction, right? So I'll just apply that, right? So you're following that much?
Yeah.
Yeah. So just remember that all the implication and the disjunctions are all branching rules, right? And here the negation of a disjunction is a non-branching rule. That's why I'm applying the non-branching rule first.
So then, yeah, you draw a line down and you write not R and not S underneath it. Is that how you do it?
That's what you do when you have progressed in the tree, but because this is just the beginning of the tree, I'll just write it as 5 and 6. Okay. So this is going to be not R, and sixth one is going to be not S. Okay. So that's just by applying the non-branching rule for this, the beta rule for this, right? So what I'll do is I will put a tick mark for this. Now it doesn't really matter which order you do it. You can just start telling me how to apply the rules and I'll just write it down.
So just to recap, so when you do a conjunction like that, it's saying that for premise 4 to be true, not R and not S both need to be true, right?
Yes.
Or, yeah. And
because you're applying, so yeah, just think of this as a beta rule, right? So beta rule for a disjunction is both of them are they are in a conjunction.
And so for both of them need to be true for the premise to be true, right?
Yes, exactly.
So then now we've got yeah, we're doing a branching and we do it on the premise 1.
Okay, premise 1. So what's the branch gonna look like?
So it's gonna be not P and Q. Yeah.
Okay. Okay, now you have the first branch. Okay. So I'll put a tick mark over here. And when you go to the second one, what you got to do is open a branch in every open branch.
Okay. So we get not RS, not RS.
Yes. So I'll put a tick over here because we are done. Okay, then.
And then here we have disjunction. So
Yeah.
so so basically in the disjunction when we branch it off, it's just how as it is. So then it's
Yeah.
yeah, just P R P R.
Oh, by the way, I forgot to mention something. We need to do this all over again. Not all over again, but like from the first rule. After every step is done, just check if there's a contradiction. So is there any contradiction here? No, right?
No.
Okay, so we can proceed. So you'll apply not R or S. Right? But now notice that there is a contradiction here.
Yeah.
So this branch is closed. This branch is closed. Right? Following?
Yeah.
Okay. Then apply the, so I'll put a tick mark over here and we'll do the next one. So next one is P or R. Right? Is
Yeah.
there a contradiction?
Just just one question. When we do like when we branch off disjunction disjunction. So it's showing that we need both P and R to be true again, right? For that premise to be true.
No, we just need one, right? Because it's a disjunction.
Okay. So we just that's what it's representing there.
Yeah.
So we have another contradiction
Where?
on the under the P, and then the R as well.
Under the P, okay. Under the R. Is there a contradiction here?
No no.
Sure.
We've got P negated R, Q negated S, negated R. I don't think so.
Yeah, you're right. Okay. So that's the important concept, that if you have a P here, oh sorry, I'll just lower down the opacity. So if you have a P here and you go like this, you need to keep going like this. So there's no contradiction on this branch. So you shouldn't go like this, like this, like this, and say, oh, there is a contradiction, because you're going like you're not following the hierarchy, right? So it needs to
Just keep on
be,
moving up.
yeah, you just need to keep on moving up. There's no bottom movement, only upward movement. So in this case, if you go like this, there's no contradiction, right? But here there is a contradiction. Sorry, one sec. Here there's a contradiction. So notice that this is open.
Yeah, so that's not what we wanted.
Yeah, so if there is a single open branch, it's an invalid argument. If there are no open branches, all the branches are closed, it's a valid argument. Now there is another concept of counter models. So when you do a truth table, how do you check validity using a truth table?
Yeah, you check the premises and that they're, you know, when the conclusion is true, the premises are all true.
The premises are all true, right? So when the premises are all true, the conclusion has to be true. And if there is a single case where the premises are true and the conclusion is false, then the argument is invalid, right?
Yeah, right.
So what we can do is, using this method, we can also get all the ways in which, all the configurations in which, if the argument is invalid, you can see which exact combination of truth values for the premises will result in the conclusion being like invalid, so the conclusion being false. So that's called like finding. So when you find that, right, when you find a case where the premises are true and the conclusion is false, that's called a counter model. It's called a counter model because you are showing that there is at least one possible world where the premises are true and the conclusion is false. But the definition of validity is that there is no such possible world. So to prove that that the argument is invalid, you need to show at least one world where the conclusion is false and the premises are true. So that's what we can find using this method as well. So let me try to show that to you with a smaller argument, because I can show it to you by truth table and truth trees. So let's take P, Q, P implies Q, not P, not Q. Okay, this is the argument. This is premise 1, this is premise 2, and this is the conclusion. And these are the propositional variables. I'll just fill them out. Okay, you know that this is going to be T, F, T, T. You know this is going to be F, F, T, T. And you know this is going to be F, T, F, T. Sorry, F, T, F, T. Right? Yeah, I think you should be comfortable with this by now. So
not Q is the conclusion, right?
Not Q is the conclusion, that's right. So how do we know that the argument is invalid?
So in line row 3,
Row 3.
the penultimate,
Yes.
penultimate one.
Yeah. So you know that the premises are true here and the conclusion is false here, so which makes the argument invalid. But I can also see that this is the configuration of truth value assignments which gives me this result. So if P is false and Q is true, and then I apply that to the rest of the argument, then I will get a result such that the premises are true and the conclusion is false.
Mm-hmm.
With a truth tree, I can find this combination as well. Let me show that to you. So let's say P implies Q, not P, not Q. Okay, sorry, not Q. So you get q here, because I just applied this double negation, sorry, beta rule over here, and then I'll just do a branching, not p or q. This branch is gonna be open, and this branch is gonna be open as well, right? So wait one second, is this gonna be open? Yeah, this is gonna be open, and this is also gonna be open. Yeah. So you have two branches in which the there is no contradiction. So let's consider this branch. Let's consider this branch. Now I'll write down every variable over here, every atomic thing here. So I'll write not p, okay, you get this? So I'm just writing down every atomic proposition. So I'm just writing not p, I'm writing q. I don't have to write not q because that is the same as q, and I don't have to rewrite not p because that is the same as not p. So every unique atomic proposition, I'm just writing it over here. Okay. So this means q is true, and this means this is true, right? So which means p is false. Okay. So if not p is true, then p is false, correct? And if q is true, then q is true. So I have this particular model over here. P is false and q is true. Now check out.
So why did you assume that not p is true?
Because like you don't have to do that, but here you are arriving at not p, right?
Yeah.
So I'm just so what happens is when something falls on this branch, it's assumed that it is true because it's like an entailment, right?
But when something falls in an open branch, we assume that these.
Whenever it falls on a branch, it sort of assumed that it is true.
Okay.
Yeah. So yeah, you can say open branch because in a closed branch you have like a contradiction. So you can say like everything on an open branch is sort of considered to be true. Yeah. So I'm considering this as true. So not p is true and q is true. But if not p is true, then p is false, right? And q is true. So I get this counter model. I'll just erase this because we have gotten what we want. So we have p is false and q is true. That's the counter model. That is one counter model. And fair enough, that's it. That matches what we found in the truth table, right? P is false and q is true. P is false, q is true. So that's the counter model.
Yeah.
Okay. So that's how you find the counter models. So let's go back to this a little more complicated argument and try to find the counter model for this.
Well, what I didn't understand on the last example is why did you decide to go on the left? Like you could have done it on the right hand side, right?
Where? Oh yeah, you can do that. You can do both ways. So even if you do it this way, you're going to reach the same thing, right? So let's do it this way. I'm writing down q. Okay.
We assume q is true.
Okay. This is the same as q, so I'm not writing it.
Then we assume not p is
true.
And then we get p as false again.
Yeah. So you get the same thing. Sometimes you get the same counter model. If there is only one counter model over here, but there are two open branches, it means that the arrangement is the same. So both ways you got the same thing. But there are arguments where you have multiple open trees because there are multiple counter models, and each one will give you a different counter model. So ideally you want to do every open branch. You, in order to get all the counter models, you need to go through every branch and pick out all the values. Okay.
Yeah.
Yeah. So let's go back to
Yeah.
this a little more complicated argument than modus ponens. Sorry, this is denying the antecedent. It's an invalid argument. So tell me, how do I get the counter model for this?
We go to the open branch that we had,
Mm-hmm.
and then yeah, we assume P is true,
Mm-hmm.
and then we assume not R is true,
I'll just write R is false because that's what
Yeah.
it means. Yeah.
and then Q is also true. S is false.
S is false.
So that's all four variables we had,
not
right?
R. Oh, sorry. Yeah. You're right. Yeah. That's all the 4 variables we had. So this is the counter model. So when you draw the truth table, and I hope you never have to draw the truth table for this, because it's gonna be what, 2 to the power 4, 2 to the 4 to the 8 to the 16, 4 to the 8 to the 16, yeah, 16. You're gonna be getting 16
Rows.
rows. So I hope you never have to do that. But yeah, so whenever, if and when you do that, whenever you go to the row corresponding to this arrangement where the P is true, Q is true, R is false, and S is false, and if you go to the conclusion, you will find that the conclusion is false.
Interesting.
Yeah. So
Pretty
that
useful.
is, yeah. So that is the connection between truth tables and truth trees. That's the relation. Is that they both will give you, they both explore all the possibilities, and both will give you the exact counter model. They'll tell you exact assignment of truth values such that the premises are true and the conclusion is false. So if you go to this row, all the premises will be true, but the conclusion will be false. Do you want to see that? We can. I can pull up an online truth table generator so that we don't have to. We don't have to do it.
Sure.
So I'll just I'll just send you a screenshot when done. P implies Q, comma, R implies S, comma, P or R, comma, R. Okay, S. Yeah.
I can't see it, but
Yeah, I'll 1 second. I'll tell you. I'll send you a screenshot. So there you go. Can you see it? I'll put it here as well. Do you see it? You can just see my screen. Yeah, you don't need to check.
yeah, I can see it.
Yeah. Okay. So let's find that row, right? Both P and Q need to be true, R and S need to be false. So that's that row, right?
Yeah. And then the conclusion is false.
Check this out. This is a premise, this is a premise, this is a premise, and this is the conclusion. Yeah? So doing this, you found the counter model.
Awesome.
Yeah. So that's all there is to doing truth trees. Now the rest is just up to practice. Depending on the argument, you might need to switch the order of the premises such that you apply the non-branching rules first, and then you apply the branching rules, and then you inspect at every. So I'll just write it over here. Apply non-branching rule apply branching rule. And then the fifth one is going to be inspect at for I'll just write it with metalinguistic variables. Okay. So this is gonna come here, and this is gonna come here as well. It's also gonna come here. So at every step where you apply a rule, you need to stop and check for a contradiction. And if you find a contradiction, close the branch. If you don't find a contradiction, apply the next rule.
What happens if you just inspect right at the end if you forget? Like, is it just to save you time, or?
Let's try that, right? Let's try it with this one. So we have already shown this is invalid, so we can just sort of get rid of this. Okay. So let's say I'm applying not R, not S. So I'm applying the first rule, which is not P or Q. Then I'll just apply not R or S, not R or S, and then I'll just apply P or R. Right? I've applied all the, basically I've covered all the, all the premises, right? So I got this tree. Now what I have is this branch is closed. This branch is closed. This branch is closed. This branch is closed. This branch is not closed. This branch is closed. This branch
is closed.
Is not closed. There's no P.
We have an S and a not S, right?
No, but we are, we are past that. So that's why you can't go further, right? Because the branch closes there. There's already contradiction there.
What do you mean we're already past that?
So when we are just applying all the rules there, right? So here we don't we have a contradiction here, but the branch doesn't close here. The branch closes here because that's where the contradiction is. But
Yeah.
we are just like we have just made a branch over there. So yeah, you can say this is closed, um, because there is a contradiction. Um, but yeah, and this is also closed. So this is the only branch which is open, right? And then you'll get
Yeah.
the counter model. But I think in this case it wasn't a problem, but maybe there are other cases where it could be a problem. Um, but yeah, like your tree just becomes very complex. Like when you go bigger and bigger, like your tree just gets really complex. So it's just better to be parsimonious. And the way to be parsimonious is to just, you know, inspect at each step.
Okay. Yeah.
Yeah. Yeah, so that's just how you can draw truth trees to check for validity and invalidity. We can talk about the other two in the next part, but yeah, this part I think we can just stop at proving validity or invalidity of an argument. So yeah,
Cool.
so that's pretty much how you do it. On to the next session, I guess.
Awesome.
Yeah. Do you want to do one last thing before we go? We were trying to do that thing by this thing, right? Like we were trying to do that argument, um, the De Morgan's law. So we are trying to do alpha, the negation of this entails um, not alpha if and only if beta, right? We can do it by truth trees. So let me just get rid of that. So this is 1. 2 will be the negation of this. So the negation of not alpha if and only if beta. So apply the rules. You can start with the you can start anywhere, it doesn't matter.
So 1 minute. So we got a biconditional negated there. So yeah, it's a branching one. So it's yeah. We have a negative alpha on the left hand side, and then negated beta
Over where?
underneath,
Mm-hmm.
and then on the other side we have beta and alpha.
Okay.
So I was just reading what the formula we wrote last time. So just in terms of just understanding it. So the biconditional is true when either they are both false. No.
No. Just apply the beta rules. Forget about that. Here we are not talking about the rules. I know, like it's like an instrument to understanding it. But for now, let's just apply the beta rule. So apply the beta rule for biconditional.
Just the one I applied for before, right?
Yeah, so you have um, the conjunction of this and not this, so not alpha and beta, and then you have beta.
I think it's because normally it's on the left hand side the conjunction of P and not Q.
Yes, so this is not alpha
Yeah,
and not
yeah.
beta. Yeah,
Is
and
this
now
what I said the first time around?
I think so. Yeah,
Yeah.
but
Okay.
you
And
were
then
thinking in terms of the other thing, right? So I just want you to apply the rule.
yeah, so then we have beta and alpha.
Alpha, right? So that's the um, first one done, right? So now you need to apply the same thing to this.
So alpha and not beta. And then beta and not alpha.
Right? And the same thing over here. Right? So now you have alpha. Sorry. You have alpha and you have not alpha. So that's a contradiction. You have beta and not beta. That's a contradiction. You have beta and not beta and beta. That's a contradiction. You have not alpha and alpha. So that's a contradiction. So this branch is closed, this branch is closed, this branch is closed, this branch is closed. Which means the argument is valid.
Yeah.
So yeah. And this is basically how you have to do for the third application to show that two well-formed formulas are equivalent. That's what we have done basically. So we have covered two things in the same thing because it's the same concept, right?
Mm-hmm.
Yeah.
So basically, to show the two well-formed formulas are equivalent, you just basically
Consider one as the premise and the other side as the conclusion, and then you draw a truth tree. The normal
okay,
way.
yeah, and then you just expand out the branches.
Yeah. And then if you find all the branches to be closed, it's the equivalence relation holds. They are equivalent to each other. If there is a single branch open, then it means that they are not equivalent. They are not logically equivalent.
Yeah, yeah, makes sense.
Yeah. So yeah, so that's pretty much it for truth trees. There is one more application which is to show that a well-formed formula is a tautology, which we'll do next time because it's very similar to this, but only slightly different. So we can cover that and do a few more examples in the next session, and then we can proceed forward to just doing some indirect proofs and conditional proofs. And then yeah, I think we should be done with prop logic.
Awesome.
Yeah. And from
Been a
there
long
on,
one.
it's just a matter of practice and keeping at it, or using it on a regular basis. That's all.
And also learning predicate logic.
Oh yeah, absolutely. But yeah.
Great. So let's call it a day then.
Yeah, we'll call it a day. It's been a long day. Cool. So I guess I'll see you in the next class. Yeah, so I'll just end the recording.